All right, so let's look at the discussion question number 7. So we saw this circuit a couple of modules ago, but now we are going to deal with it in a slightly different way. So now we're going to be dealing with a forcing function that really can only be dealt with using Laplace transforms. So let's get started. So let's write the equation first in our time domain form. So what are our component values? So L is our inductor, so that's 100 millihenries, so 0.1 Q double prime. R is a 1,000 ohm resistor, so plus 1,000 Q prime, plus 1 over C, so 1 over 1 microfarad, so 1 over 10 to the negative 6 Q equals, for now, I'm just going to call it V of T. Let's clean things up a little bit more. So 0.1 Q prime plus 1,000, sorry, Q double prime, plus 1,000 Q prime plus 1,000,000 or 10 to the 6 Q equals V of T. What the heck is V of T? So let's draw a graph of what this looks like. So behaves as follows. At 2 seconds, the voltage increases linearly to 24 seconds over the next 12 seconds. So T equals 2, T equals 14, and then we're starting at 0 volts, and then it goes to 24 volts. So basically we have this, ramp function or, linear function. So here's my forcing function. It's going to go like that, but then what happens at 14 seconds is it's going to basically be shut off. So after 14 seconds, my voltage goes to 0. Okay. So how do I deal with that? Problem with that is this. This function is not even defined from t equals 0 to t equals 2. This function is not continuous at t equals 14, which means I can't even talk about its derivative. So if a function is not continuous, it's not differentiable. So in the time domain, this function is not, I can't really analyze it using all my, pre-Laplace transform tools. So we have to transform this function. So before we do that, we should probably define it in the time domain. And I think the way we have to define that is, not have to, but I think the most direct way is through a Laplace, or sorry, a piecewise function. So what is the slope? And this is a linear function. So what's the slope of this line? Well, it goes to 24 volts. It increases by 24 volts in a span of 12 seconds. So I think the slope is going to be 2 volts per second. So y equals mx plus b. Y equals 2x plus b. And then to find the y-intercept, if I know a point, I'll be okay. What's a point I know? Well, I know that at time or x equals 2, y equals 0. So I believe that tells me that b equals -4. All right, so what does that tell me? That tells me that for the part of this function that has that diagonal line on it, this is y equals 2x minus 4. All right, so now, how can I talk about this function? So I believe this function it can be defined as 2t minus 4, but over what subdomain? As long as 2 is less than or equal to t, which is less than or equal to 14. and 0 otherwise. So I have this, one-time pulse that's forcing my circuit here. So how do I do a Laplace transform of this function? So let's talk about it both ways. There's the manual approach and there's the table approach, and I think both are good to talk about. So let's do the manual approach first. So the Laplace transform of any time domain function is equal to the integral from 0 to infinity of e to the negative st times f of t dt. And now I'm starting to second guess myself. Is it e to the negative st? What is the Laplace integral? The Laplace transform integral is, okay, the integral from 0 to infinity of e to the negative st ft f of t dt. All right, so this is the integral that will give it to me. And like typically I would integrate from 0 to infinity, except for my function. I'm not integrating a function that even exists or that is even non-zero, for all positive values of t. So because of that, how do I basically account for the fact that, my function is 2t minus 4, but it's only 2t minus 4 sometimes. So let's handle that last. Before then, let's drop in the rest of the Laplace transform, the rest of the ingredients I need. So e to the negative st times 2t minus 4 dt. I'm not going to integrate from 0 to infinity because this function is not, I can't define this function as 2t minus 4 from 0 to 2 or from 14 onward. So I'm only going to integrate it over the time where it actually fits the f of t that I'm calling it. So that 2t minus 4. So this is the integral I'm going to compute to get my Laplace transform. So the integral from 2 to 14 of 2t minus 4 times e to the negative st dt. I think we're going to need integration by parts for that, so let's set that up. So the integral of u dv is equal to uv minus the integral of v du. I'm going to call u the linear part. So u is equal to 2t minus 4, which means du is going to be 2 dt. dv is going to be the rest of it, e to the negative st dt, which means v will be equal to negative e to the negative st over s. Okay, so now, for now, I'm going to worry just about the antiderivative, and then I'll deal with the limits later. So uv becomes this, negative 2t minus 4 times e to the negative st over s minus the integral of v du. So minus the integral of negative 2 e to the negative st over s. I'm going to go ahead and cancel out these two negative signs. Okay. dt. And then what does this integral become? So negative 2t minus 4 e to the negative st over s this integral here, if I integrate again, I'm going to get minus 2e to the negative st over s squared. So I believe that's my full integral. So I'm kind of taking some shortcuts just in my notation. So from here, what am I going to do? I'm going to plug in my limits of 14 and 2. And get my picture out of the way. All right, so when I do that, what do I come up with? Yeah, where do I have room left? Let's get rid of some of my integration by parts bookkeeping here. So negative 2 times 14, so negative 28 minus 4. So minus 32 times e to the negative 14 over s minus 2e to the negative 14s over s squared minus whatever happens when I plug in 2. So 2t minus 4, that's 0. So the entire left-hand term vanishes. Then when I plug in 2 for the other bit, I get minus 2e to the negative 2s over s squared. So I believe this is my complete transform after I do some cleanup. Did I lose a t? Or did I lose an s? Yeah, it should be negative 14s, right? Negative 32. Well, that's not 32. 28 minus 4 is 24. Broke some PEMDAS there. Let's just double check the whole thing one more time. When I plug in 14 for t, I get 28 minus 4, 24, so negative 24 e to the negative 14s over s minus 2e to the negative 14s over s squared. And then when I plug in 2, this becomes 0. And this becomes 2e to the negative 2s over s squared. All right, so now this equals negative 24 e to the negative 14s over s minus 2e to the negative 14s over s squared plus 2e to the negative 2s over s squared. So this weird thing is my no longer v of t, this is my v of s. Okay, so, and again, what's the point of a Laplace transform? It lets me turn my time domain function, which has discontinuities in it, into my Laplace domain equation, my S domain function, which is made up of, these exponent, like this sum of exponential terms. Exponential functions, those are continuous everywhere. And then I divide those by s or s squared. Those are continuous everywhere except for s equals 0. So when I have discontinuities at the start of my domain, that is a much easier proposition to deal with than if I have discontinuities in the interior, like t equals 14. That's right in the middle of the domain. That's, I want to start investigating this where time equals 0. So the fact that I have discontinuities or I have a point where my function is not differentiable at 2. I have a point where it's not even continuous at 14. That's why I need the Laplace transforms to help me out here. All right. So I think I've gone beyond what part one asked me for. I think I've solved this equation. So now let's go ahead and move on to part two. All right, so let's go ahead and keep on going. So we're going to go to a new slide to get some more space. But having the Laplace transform for our voltage source is crucial. So moving on, let's remind ourselves now of, try to save some more space. So 0.1 Q double prime plus 1,000 Q prime plus 10 to the sixth or 1 million Q equals V of T. So like we just talked about, I can't solve this equation using, conventional time domain approaches. So because of that, I'm going to Laplace transform both sides. So Laplace transform this side equals the Laplace transform of V of T. All right, so what is the Laplace transform of Q double prime? So maybe I should pull up the table. So let me go find that. All right, so here's the table. Bringing this up to remind ourselves how to take the Laplace transform of a first and second derivative. So Laplace transform of f double prime is this s squared f of s minus s f naught minus f prime of 0. So one thing we need to know before we go forward is let's write down our initial conditions. So what is, let me go back to I don't want to write in black. Keep red. What is Q of 0? Solve this equation given that initially no charges flow to the circuit and there's initial current of 100 milliamps or 100 millicoulombs per second. So that implies that Q of 0 equals 0 and Q prime of 0 is 100 milliamps or 100 over 1,000 or 0.1. Okay, so now that we're going to transform this, we got 0.1 times the Laplace transform of Q double prime, which is what? S squared f of s so s squared, I'll call it Q of s minus s minus f naught minus f prime naught. Okay. So minus s times Q naught, which is 0, minus Q prime of 0, which is 0.1. Okay, so that's the Laplace transform of the second derivative plus 1,000 times Q prime. So how do we deal with that? I believe it's S times Q of S minus Q of 0, so that'll be 0. Plus 10 to the sixth times Q, which is, that just gets transformed to Q of S. And I want to double check that, so let's go back. I just want to make sure that I am correct about how the first derivative, yeah, SF of S minus F naught. Okay, so we're good there. So we should have everything we need now. Okay, so that is all the left-hand side of the equation, and this equals what? This equals whatever we said the Laplace transform of our voltage source was. So 2e to the negative 2s over s squared 2e to the negative 2s over s squared minus 2e to the negative 14s over s squared minus 2e to the negative 14s over s squared minus 24 e to the negative 14s over s. Okay, so this long thing here is our Laplace transform. So what's our goal with this thing? Our goal is to solve for, basically isolate Q of S. So we have kind of a long way to go, but I believe some things are going to fall off here. So this is S times 0, that's 0. Got some zeros in here, so let's start eliminating brackets. So 0.1 S squared Q of S minus 0.1 times 0.1, so 0.01, plus 1,000 S Q of S plus 10 to the 6th Q of S equals our forcing function, 2e to the negative 2s over s squared minus 2e to the negative 14s over s squared minus 24e to the negative 14s over s. All right, so now what? Again, we want to isolate Q of S, so I'm going to keep everything that has Q of S on the left-hand side of my equation, move everything else over. So what needs to be moved over? Really just the negative 0.01. So I'm going to add 0.01 to both sides. Let's go ahead and call this plus 1 over 100. All right, so then what do I have? On the left, I can factor out Q of S out of a bunch of terms. So if I factor that out, I have 0.1 S squared plus 1,000 S plus 10 to the 6th equals all this other stuff. So 2e to the negative 2s over s squared minus 2e, let's move that up a little bit, 2e to the negative 14s over s squared minus 24e to the negative 14s over s plus 1 over 100. Okay, so kind of a gross looking equation, but that's okay. So now what's going to happen if we isolate Q of S? Trying to wonder if it wouldn't be in our best interest to, let's handle one thing at a time. So now let's solve for Q of S. Q of S equals this. Actually, I take it back. I'm going to take the right-hand side of this equation. I'm going to put all these, I'm going to consolidate all those by finding the common denominator. So what is a common denominator here? I believe I can use 100s squared. So if I give everything a denominator of 100s squared, then my first term becomes 200 e to the negative 2s. My next term becomes minus 200 e to the negative 14s. This next one becomes minus 2400 s e to the negative 14s plus s squared. All right. So now what happens if I divide off Q of S? Q of S equals this totally not intimidating function, 200 e to the negative 2s minus 200 e to the negative 14s minus 2400 s e to the negative 14s plus s squared all over 100s squared times the stuff I'm about to divide by, 0.1s squared plus 1000s plus 10 to the 6th. So this is my Q of S. So what? What does this tell me going forward? All right, so now that we have this this Q of S, so this is a very involved function that we have. I believe we could do the inverse Laplace transform on this by hand if we did partial fraction decomposition. I'm totally happy if we instead take it to Wolfram, which I have done here. So here's the result. So yeah, there are better uses of our time than finding this, very involved time domain function. But what I really want to look at here is, and you're not going to let me enlarge without paying for stuff, aren't you? Yeah, that's what I thought. So I'll enlarge as much as I can. So here's my plot here. This is what my function Q of t looks like. So, how many coulombs am I looking at here? Just qualitatively, what I want to look at is this. We start out at, even though we said the initial charge was absolutely 0, we do see a little spike here, and that's because we started with some current. So because of that initial current, we're going to see some charge moving through the circuit. It's going to dissipate very quickly. And then we're going to see no charge at all moving for the next for the first 2 seconds. And then what happens in 2 seconds? Essentially, our voltage source turns on. So when our voltage source turns on, now we're going to see our charge kind of happen at this linear rate. But, we're seeing a linear rate, but it is not the same rate that, our voltage is increasing by 2 volts per second, essentially. We're not seeing that same rate here. Also, we're seeing, as we expected, precipitous drop-off. So this second plot here looks a little further out in time. And we see this drop-off in the amount of charge that's flowing, when t gets to 14 seconds, because that's when our forcing function essentially stops forcing. All right, so very, very involved Laplace transform activity here, but yeah, that is all for discussion question number 7.